Welcome to today's paper reading. Today's paper is titled, Accelerating Image Generation with Subpath Linear Approximation Model. This paper was published on AR14 by Chen and colleagues from Nanjing University and Alibaba Group. The abstract highlights the advancements of diffusion models in various generation tasks but points out their slow inference speed as a limitation. To address this, the authors proposed the Subpath Linear Approximation Model, SPLAM. This model accelerates diffusion models while preserving the quality of generated images by utilizing subpath linear ODEs. The experimental results show that SPLAM can produce high-quality generative models within 100 GPU days, enabling 2 to 4-step generation. It also outperforms existing acceleration methods, achieving state-of-the-art performance in terms of FID and image quality. Diffusion models are known for their ability to synthesize high-quality images through a process of progressively refining random noise into structured visual content. However, this process is computationally intensive, often requiring many iteration steps. Consistency models address this by ensuring a consistent denoising mapping across probability flow ODE trajectories, but they face issues with error accumulation. To tackle these challenges, the Subpath Linear Approximation Model, SPLAM, is proposed. SPLAM uses subpath linear ODEs to approximate these trajectories more accurately, reducing cumulative errors and improving image generation quality. Additionally, SPLAM includes an efficient distillation method that can be integrated with pre-trained models like Stable Diffusion, enhancing training efficiency and performance. Figure 1 illustrates the methodology of our Subpath Linear Approximation Model, SPLAM. The model uses subpath linear ordinary differential equations, ODEs, to approximate the subpaths on the probability flow ordinary differential equation, PF-ODE, trajectories. This approximation is achieved through linear interpolation between the corresponding endpoints of these subpaths. The SPLAM is then trained based on the consistent mapping along these subpath linear ODEs, SLODS, to minimize the approximated errors. This approach allows SPLAM to construct denoising mappings with smaller cumulative approximated errors, thereby enhancing the quality of image generation. Diffusion models have become a cornerstone in generative models, particularly known for their ability to produce high-quality, detailed images. These models operate using a continuous time stochastic differential equation, SD, that iteratively denoise an initial noise distribution. The reverse diffusion process is particularly effective at capturing complex data structures. However, the generation speed of these models is a significant limitation due to the need for thousands of sampling steps. To address this, various acceleration techniques have been developed. Some focus on designing non-training fast diffusion samplers, reducing the steps required from thousands to 20 to 50. Distillation methods aim to condense the inference steps to fewer than 10, with progressive distillation showing particular promise. Additionally, emerging models like consistency models and InstaFlow propose new approaches to further streamline the generation process, including one-step generation capabilities. Diffusion models transform data into a noisy state through Gaussian perturbations and reverse this process to reconstruct the original data. They are also known as score-based generative models. Consistency models, on the other hand, project solution trajectories back to the starting point, ensuring self-consistency. Latent consistency models integrate these concepts with V-encoder-decoder pairs and employ a skipping step size for accelerated training. The one-step denoiser employs a neural network theta, xt, t, to predict a standard Gaussian distribution, implementing the denoising mapping f theta, xt, t. Consistency models address issues by leveraging the consistency property, yielding an approximated error estimation. The Subpath Linear Approximation Model, SPLAM, introduces subpath linear, SL, ODEs for linear interpolation, providing a progressive estimation for DIST increment and improving generation quality. The experimental evaluation of the Subpath Linear Approximation Model, SPLAM, demonstrates its superior performance across various metrics. Quantitatively, SPLAM significantly outperforms baseline methods in terms of FID and CLIP score, showing consistent results across different test sets. In ablation studies, the effect of varying skipping step sizes and the associated training costs are examined, revealing SPLAM's ability to maintain high image fidelity with large steps and its efficient convergence. Additionally, the error estimation study validates SPLAM's effectiveness in minimizing approximated errors. Qualitatively, SBLAM produces high-quality images efficiently, even in fewer steps, and compares favorably with state-of-the-art models. These results collectively highlight SPLAM's robust performance and potential for practical applications. Table 1 presents the quantitative results for the SDV 2.1 base model with a guidance scale of 8. The table compares the performance of SBLAM against baseline methods such as DDIM, DPM, DPM++, and LCM** on the LAILN test set, as well as our reproduction of LCM with a fixed guidance scale. Additionally, results on the COCO 30K test set are included. The key findings show that SBLAM consistently outperforms these baseline methods across both test sets, achieving lower FID scores and higher CLIP scores at each sampling step. This indicates that SBLAM not only maintains high-quality image generation but also does so with fewer sampling steps, demonstrating its efficiency and effectiveness in accelerating the diffusion model. Table 2 presents the quantitative results for the SDV 1.5 model. The baseline numbers for comparison are cited from 50 and 49. All the results of LCM are our reproduction, ensuring that the performance aligns with the stated criteria in the paper. Additionally, results marked with are evaluated by us using the released models. This table provides a comprehensive view of the model's performance against established baselines and our reproduced methods. Figure 2 presents key ablation studies and training performance comparisons between LCM and SBLAM. Part A focuses on the effects of varying skipping step sizes and the introduction of the multiple estimation (ME) strategy, which significantly enhances performance. In Part B, the training curves demonstrate that SBLAM, especially when configured with a step size of 100 and the ME strategy, converges more rapidly than LCM. Finally, Part C evaluates the error delta between consistency mapping values of adjacent points using the PF-ODE method, showing SBLAM's consistent superiority over LCM in error reduction. Figure 3 illustrates the impact of varying the guidance scale W on SBLAM. Part A provides a visualization of how different values of W affect the performance of SBLAM. Part B shows the trade-off curve as the guidance scale W increases from 3.0 to 12.0. While a higher W value enhances sample quality, as indicated by CLIP scores, it also results in a decline in FID performance and oversaturation. This analysis highlights the critical role of the guidance scale W in balancing the semantic alignment and the quality of the generated images in SBLAM. Figure 4 presents a comparison between our SBLAM and LCM 26 in 1, 2, and 4-step image generation tasks. The results from LCM are based on our reproduction, as detailed in Section 5.1. Our SBLAM consistently produces higher quality images that are notably clearer and more detailed. A significant observation is the exceptional performance of SBLAM in the 2-step generation, which closely matches the 4-step generation results of LCM. This highlights the efficiency and effectiveness of our approach in creating high-fidelity images with fewer generation steps. Figure 5 presents qualitative results comparing the generation quality of SBLAM with other models. The text prompts used are sourced from DMD and Diffusion, with results from these papers also included for comparison. Notably, SBLAM shows the highest generation quality in 4-step generation, except when compared to SD models. Even when the sampling step is reduced to 2, SBLAM maintains a performance level that surpasses the 4-step LCM. Additionally, SBLAM, distilled from SDV 1.5, is compared against the most advanced accelerating diffusion models, demonstrating its superior generation quality across existing methods. In this paper, the authors propose a novel approach called subpath linear approximation models, SBLAM, to accelerate diffusion models. SBLAM utilizes the approximation strategy found in consistency models and treats PF-ODE trajectories as a series of interconnected subpaths. This approach is guided by the optimization direction charted by each subpath, enabling progressive and continuous optimization of the approximated learning objectives. This results in the construction of denoising mappings with smaller cumulative errors. Additionally, the authors develop an efficient distillation procedure for SPLAM to incorporate latent diffusion models. Extensive experiments on LAION, MS COCO 2014, and MS COCO 2017 datasets consistently demonstrate the superiority of SPLAM over existing accelerating diffusion approaches in few-step generation scenarios, with fast training convergence. This research is made possible by the generous support from several funding bodies. The primary support comes from the National Key R&D Program of China, under the project number 2022 ZD01609000. Additional funding is provided by the National Natural Science Foundation of China, with project numbers 620761119 and 619210006. The research also benefits from the fundamental research funds for the central universities, specifically under the number 020214380119. Furthermore, the Collaborative Innovation Center of Novel Software Technology and Industrialization has been instrumental in facilitating this work. In this appendix, the common settings for the text-to-image generation task involve using pre-trained stable diffusion models, specifically SDV 1.5 and SDV 2.1 base, as teacher models. The training dataset is a subset of LAION 5B, known as LAION Aesthetics 6+, which includes 12 million text-image pairs with high predicted aesthetics scores. The DDIM solver is chosen as the ODE solver with a uniformly set skipping step size of 20. The training process utilizes the Atom W optimizer with a learning rate of 8 times 10 to the power of -6 and a weight decay of 0. Gradient clipping and exponential moving average (EMA) are applied to ensure stability. The models are trained with a batch size of 1024 distributed across 16 A100 GPUs. For evaluation, the Freshet inception distance (FID) is used to measure image quality, and the CLIP score is used to measure text-to-image alignment, calculated using LAION OpenClip VTG/14. Figure 6 presents a comparison of generated samples using a two-step process from our SPLAM and LCM models, both distilled from DreamShaper v7. The generation leverages the LCM DreamShaper v7 checkpoint available on Hugging Face. This figure showcases the output of both models on various prompts, highlighting the differences and similarities in their text-to-image generation capabilities. Figure 7 presents a comparison of generated images using a four-step process from two models, SPLAM and LCM, both distilled from DreamShaper v7. The images are generated using the LCM DreamShaper v7 checkpoint hosted on Hugging Face. The figure showcases the results of generating images based on various textual prompts, highlighting the differences and similarities in the outputs of the two models. This comparison is crucial for evaluating the effectiveness and efficiency of the four-step generation process in each model. Table 3 presents a comparison of the optimized performance between direct linking ordinary differential equations, DL-ODEs, and subpath linear ordinary differential equations, SL-ODEs. The table reports the four-step generation results for all methods with a guidance scale W equals 8. Key metrics include the Freshet inception distance, FID, for 5K and 30K images. The results show that SL-ODEs, specifically SPLAM, achieve the lowest FID scores, indicating superior image generation quality compared to DL-ODEs and LCM. This demonstrates the effectiveness of SPLAM in generating high-quality images with fewer steps. Thank you for watching.